Good morning. Our presentation here is about the shaking table test of the continuation of a program that initiated by Professor Steve Main on bridge columns and basically moving away from the conventional system of having a column, forming a plastic hinge, and finding all the damage limit states, spalling and bar buckling, ultimately bar fracturing or so, which we know more or less for Caltrans columns this is occurring at a certain drift level. So the main idea here behind is how can we build things with techniques of advanced accelerated bridge construction, meaning that we can precast these elements and put them together overnight to get out to have the least amount of impact in the construction site and in the traffic accidents and so on. So let me see, what we have here is the phase one of this project. We had teams from University of Washington, from the University of California, Berkeley, and UC San Diego. The idea was to come with similar specimens. Each one had different types of connections to the foundation. The columns were in cantilever mode, and we subjected these columns to two components of horizontal ground motion. In parallel, and not necessarily part of PIER, was a test done at the University of Reno, Nevada, on a complete system with bridge columns and so on. And they were subjected to horizontal components of the ground motion with connection systems that were developed by Professor Stanton and Eberhard at the University of Washington. So where do we want to move on from here? We have systems here. We have the bend cap that is not present here. We just have the mass. We have a foundation, we have a column, and then we have the connection. In these systems, the connection plays a very important role. How can we make it that these connections can basically take it with low damage? That's the idea behind moving away from what we have, moving into low damage. So we can basically form a kind of dislocation at a certain plane, and it can go on practically forever at very large displacement, very little damage. That's the idea behind. In our case, in San Diego, we came with the idea of a socket that we can use a pipe, a steel pipe, and during the fabrication of that pipe, we will leave a little fuse that we will cut off. You will see it later on, and that will form the plane where rocking will take place. And what we wanted to do in this phase with our colleagues at Berkeley is come up with move the system forward, not only look at a cantilever column or something, but look more or less into a system. We look at a bridge that is in close proximity of the San Andreas Fault in San Bernardino. It's about 5 kilometers away. It's a 4-column bent. But of course, if we are going to replicate this bent on the shaking table here at UC Berkeley, because we have the vertical component here, is we will have a very small scale. So what we did here, basically, we are interested in the exterior columns because we have the fluctuation of the axial force. Yeah, so these are not interior columns anymore, and we are also interested in that there will be subjected to a point of inflection in the middle. So the idea is basically to position the two columns. This is the specimen here, so that in the analysis of the 4-column bend, we have more or less the same fluctuation of the axial forces. It's just matter of finding the separation between the two columns. So once we found that, we size the columns, we size the specimens to fit the specifications of the shaking table and maximize everything that we could have vertical and horizontal in the shake table here. This is the bend cap. So what we do, we precast the entire column. And then we want to socket that column in the foundation as well as in the bend cap. And for that, we just leave a corrugated drainage pipe. And the advantage of that helical coil that we have here is that we can actually oversize the pipe, embed the column there, and then we grout. So we can transfer the shear force with no major issues. We have ample tolerances. We don't have any issues with the tolerances there. We cater and design for tolerances as opposed to see what happened in the field and then scratch our heads because things do not fit in place. So these are the columns. The columns can be manufactured in a precast concrete yard, can also be manufactured in the field. They can be pre-tension, they can be post-tension. And the trick here is that although you see a single column here, that column is actually made out of five little pieces. Two exterior pieces where we have a series of weld bits, internal and external, to transfer shear. One long piece, which is basically what you will get to see on the bridge itself. And then a little ring that is cut and then put back in place, and it will act initially as a part of the form, then we peel it off, and that will form basically the plane or rocking at the interfaces at the two column ends. Inside, we have reinforcing bars that will act as energy dissipation devices, and the fact that those bars are confined by the external shell, that means that those bars find a very difficult way to buckle. Essentially, if we put strain gauges there, you will see on the outer shell barely any yielding will occur, only very late in the game. So when we talk out here about low cycle fatigue, in reality is no low cycle fatigue. What's happening is buckling of the bar that is basically going to end the life of that bar. Is going to buckle, and then once we stretch, the bar will go on fracture. But if the bar cannot buckle, we can take it for a long time before actually that bar goes and fractures. These are some construction techniques. You can see the upper part, we have the weld bits. We are peeling off here the ring that we place there for temporarily to cast the column. Once it's removed, you can see it leaves a little gap there. Then we embed the column. This is in the lab here in front of this room. So we have the foundation, we socket the column there, we grout the column, and then we bring the cap on top and repeat the operation. Here's the grouting of this. You can see it's highly oversized to give ample tolerances as so. You can see here the positioning of the bend. Very easy. We just drop it there and then we grout. At the end, well, we also need to furnish a lot of safety devices. In this case, we wanted to excite this in one longitudinal direction. We did not want to excite in two components, but only in the longitudinal or transverse direction in the bridge, as well as in the vertical direction. We added mass, and we placed a number of restraint frames basically to control the torsion in the specimen. We subjected this, and I'm not going to go into details here, but we subjected this to 12 tests, some of them representing low intensity motion, some of them representing what Caltrans calls the design motion, way beyond the design motion, and way beyond the design motion, going back until we basically fracture the reinforcing steel. You can see a test here. This is what we call the design test for Caltrans. I'm going to go slowly here. And if we turn the lights off, is it possible, Salim, to turn the lights off completely? Because I just barely see it. Add the fact that I'm colorblind, I don't see the red. So here we have the base shear, and we have the drift ratio of the column. So what you get to see, if we're doing a static test, a quasi-static test, you see a recentering response. And the dynamic conditions, we actually have the recentering at the end of the test, although we see some of the response going through quadrants 2 and 4. But this doesn't mean that it's no recentering. It will go and recenter as I will show you. With the vertical one, we have here the axial force on the masses at the top of in the bend cap, and versus the uplift of the mass. So in actual, the maximum uplift of the bend cap occurs when we have the maximum drift due to the kinematics. So that means that if we had the maximum axial force somewhere here, like here, we have a very high spike. Those two things, maximum drift and maximum axial force, are nearly concurrent. So we chose some motions that will be the case, and some motions that were totally decoupled. Those was part of the selection of the ground motions. We want to see what happens in these cases where we are also vertically accelerating the mass, not only because of the kinematics moving the mass up and down, but also to the input ground motion. So these are basically the input and output accelerations at the center of mass. This is horizontal and this is vertical. So let me replay this one. Is there any audio in the video? So, because it's kind of nice to see when it goes, just the noise makes part of the symphony, I guess, in these tests. And nice also that Steve was there in this test. He was already pretty sick. He said, look, I'm dizzy, I need to sit down, but I will gladly watch the tests. That makes it different, isn't it? So you have the shaking table moving up and down and all the noise and whistles. So in this test, we go to a modest 4%, which is what Caltrans wants to do plus more or less in the design stage. Can we go beyond that? So you go and inspect what's going on here, and you see nothing, no damage, zero. You see the joints where we basically peel off that ring. You see some little debris from construction, and that's pretty much it. So let's go to a bigger one. So here we are going to 8% drift ratio, and it's kind of nice. Nothing happens to it. So it's basically what we are seeing here. Not only we have no damage, but the effect that the column is post-tension and we are maintaining that post-tension force, the column goes back and recenters. There is no residual displacement of any kind of well, there is very little residual displacement. You can see these here. These are the drift ratio. So for Earthquake 5, the first video we saw, we attained about 4%. And the residual drift ratio is 0.1%. One could say, well, this is part of the input ground motion you put, and the ground motion recenter the whole thing. But you can see that systematically here, all the ground motions that you have, apart from the high demands, you will have very small residual displacement because it's engineered to recenter. Here we have Earthquake 8 and 9. We're getting 8% with no damage. We keep going up and down like an aftershock, and then more or less, until in the end, we were fatiguing indeed those bars, and we saw the loud pops of the mild steel bars breaking away from the specimen. So if we see, this is a little bit more complicated. This is the vertical axis is the percentage of the stresses as a percentage of the ultimate stress in the bar. So you can see here we post-tension the bar to about 40%, which is different from what we do in practice. With pre-stressed concrete, we try to pre-stress these things to 70, 80%. Then through losses, we get to about 65%. Here we have low post-tension because we want to maintain that tendon elastic as much as we can. So we go to about, in the test, we go to about 7% drift ratio, and boom, we see a little bit of loss in the pre-stressing at the end of the test. The gray bar here means that the bar, due to the kinematics, the column is elongating and that tendon is stretching elastically and then goes back. Right? So we have an elastic tendon all the way here, but here in Earthquake 8, we attain about 7% drift ratio, and then we lose a little bit of pre-stressing. And the reason for that is not so much that the whole tendon elongated, but the tendon, the bar, basically bare and bent a little bit and lost a little bit of the pre-stressing force. So that once that happens, is maintained, we don't lose any more pre-stressing. And that's kind of important at the level of the model. That was something that surprised us when we were doing the our own internal analysis, because we had used a truss element and we had lost the pre-stressing force. But the moment that we changed for a beam element, we saw that we have partial bending was due to bearing of that bar against the concrete itself. Very interesting. No damage means very low downtime or no downtime, which is something that here at Pier is something that we would like to see.
Bonded or unbonded?
Unbonded, yeah. Sure, that's a good point. It's all unbonded. The moment we have bonding of the tendon, we basically are asking for early yielding or so. It's totally unbonded from end to end. So these are some photos at different levels. You can see at the end of the test, that's the interface in earthquake 9, and you see some debris. It will not be honest to say there is zero damage, but you see very little damage or something you broom out, and that's it. There is no crashing of the concrete because the confinement is so large that the arching is very little. So you see a little bit of a spalling of that arching of the concrete, and that's it. That's pretty much it. As part of this exercise, Salim and Professor Mosalam were working in an effort to get a blind prediction for this unit. So we kept high secrecy on what we were doing. We did our own internal models and predictions by hand, in fact, some of them, which is something that it will crop up in a minute. It's my opinion, once you have gray hair, you want to do some predictions by hand to benchmark yourself, as opposed to entirely rely on the computer. But we had both. We had both exercise hand and as well as OpenSys models. So we invited people to predict the response of these displacement demands for every input ground motion as it was measured during each of the tests. Shear forces, whatnot, a series of questions. And I would like to show you two of the results that we have. So here we look at these basically drift ratios of lateral displacements. And one of the things you see is it's kind of large dispersion. So that's something that we again need to sit down with these blind predictions, sit down with the community and say, why are you getting such large dispersions when you could nail this more or less by hand? So one of the things you could do is look at the displacement response spectra, get your period. You can do an elastic model if you want, account for some loss of stiffness, do some basic handheld calculations, and nail the problem within plus or minus 25%. And it takes 10 minutes. And when we see, for example, in earthquake 3, yeah, there are very good predictions, of course, but there's some large dispersion that we would like to see. Is that are you making a systematic error in your model or what's going on? But the idea of benchmarking these things by hand is not a bad idea. I think it has to be reinforced again. In the last test, of course, it's all over the place. You see, we basically have from zero response to very large response. So the dispersion increases as we move forward in the test because the nonlinear response make it more difficult for you to predict. And when we go to, of course, in these exercises, displacements are much easier to predict than forces, right? So when you go to forces, or even if you were going to go down and try to predict other quantities or so, like we were talking about the strains or so, it will really blow, you know? So you go now to the second level, which are forces, and you see the large dispersions here. Interesting from the point of view of blind prediction, sit the community and try to learn one another what's going on.
It would be interesting to have different colors for the crosses just to see a particular team wearing.
Yes.
We have that.
Yeah, we have that. We didn't put here, but that's something that I did with Ali.
Actually, Jose suggested that because we saw very strange things, like somebody
That's why I was
even made
kind
a
of curious.
mistake.
Yeah, I was curious.
Yeah,
Made a mistake on the pre-stressing force. That's like a given number, but you see it systematically going through their calculations. So they just made one error that propagated.
you have to filter this And you have, first of all, in the low-level predictions, you have to filter those whose axial force is kind of wrong, is that they basically put the wrong mass or the wrong, I have no idea, but you have to filter those out. We are in the process of working with Salim to filter those out that really started with low quality control in the model from those who did a good job, and who knows what's wrong in the non-linear model. But it's still there and can happen in an office or so when we are beginning to rely more and more on predictions just to see that these things do happen, that there is dispersion or human uncertainty in these models. So I don't want to read through these things, but I think the experiment was an excellent exercise to show Caltrans and other DOTs the significance of these new systems, where we basically look at very low damage, look at a bridge that can be basically put back in operation right away without need to shore or inspecting that bridge. So it's moving to new technologies together with menus like seismic isolation. These are basically avenues that can be utilized for new construction or so. So with careful design, you can basically prevent yielding of the unbonded tendon or delay that yielding of the tendon, as well as of the reinforcing steel that is providing some energy dissipation. And you do need a little bit of energy dissipation. You don't need a lot, but you do need something, otherwise it becomes very unpredictable. It becomes a rocking body whose response can be very sensitive to some input ground motions and less sensitive to others. So once you put a little bit of hysteretic energy dissipation, it becomes rather predictable. From the blind prediction, as I say, well, I think one of the major takeaways is not bad to try to predict these things by hand. Try to form a mature or rough decision before you actually check your model and go crazy with it. It's something that once you have kind of gray hair, you believe on it somewhat, and you try to bound your solutions, and it's a pretty useful exercise. I would like to acknowledge all the peer personnel. Everyone was greatly involved here. All the peer personnel, lab personnel, they worked tremendously in this project. It was a fascinating, excellent experience. Administrative staff, technicians, my peers here at Berkeley. It was a very fun project to work in. Arpit, who is the student sitting here, he showed up with a tie this morning, and the professor showed without any tie or so. But he indeed knows the intimate details of everything that goes there. So if you can ask him what was he looking for, he will tell you exactly. So I'm sure you will be able to answer any questions, Harpreet. And he is the one who did all the work, I must say.
Is this in compliance with our safety?
He's probably looking for the hard hat.
There is a hard hat in there.
Thank you. John.
What are the foundation requirements for this system? How much can the foundation move on a real project in terms of its performance to make sure that your structural system works appropriately?
There are two kind of things. You can have a shallow foundation like this, and you will not allow it to rock. You have the rocking above the interface.
Is there in that shaking table test, obviously you did not rock at all, it went with the ground. But in terms of permanent deformation, is there some maximum transit rotation?
Yeah.
Maximum permanent rotation that you make?
I would expect, John, to be up of the order of 0.3% radians or so, maximum. If you go above that, you have a very flexible foundation. But that's a number that I wouldn't be surprised you agree that's probably a maximum rotation of the ground or so. If you are having very large overturning moments on other kind of soil, you may want to pile that foundation to resist the overturning. Yes?
This is a question in general on some of these shaking table experiments. To what extent would it make sense to use an in-ground motion for the table rather than a record from, rock acceleration from someplace. Because, I mean, in structural engineering, that's a typical thing. You take a ground motion from someplace and just feed it in. Of course, filtered so that the
Right.
table can handle the frequencies. But my point here is that it's very difficult to put a soul box underneath because you cannot get the mass. Okay? And so one alternative is to actually say, okay, we have a deep site, 30 meters of soil. Let's propagate the motion through the 30 meters and feed that motion into the table, and then you can model an actual ground response for the shallow foundation.
In this shaking table, we could actually exercise the rotational degree of freedom if we wanted to. Totally. Totally agree that we could actually propagate and get some rotational component as part of the input ground motion. I agree with you on that, totally agree. However, if we put this on rock only or so, the low frequency content is not there. So you will go and this thing is just going to go forever with no excitation. So, and we want to shake it.
Most of us don't care very much about rock.
Right. So rock is like away from this. So the question is now, do we begin, and this is very important for PA in my opinion, do we begin to look at the rotational input ground motion? And I think it's quite important. And it is not only important for this, as you point out, but how about tall buildings? And you get a fishing cane and just excited like that, and that guy at the top is going to go nuts, So you are pointing out a very important problem, and it's something that opens avenues for us not only to look at three components of the ground motion, but look at perhaps the 5 of them, and 6 if we want to look at the torsional as well.
And as an intermediate, exactly. And as an intermediate way of approaching this, you can always bring the possibility of doing hybrid testing.
Well, that's essentially a hybrid test. I mean, at one point we proposed a table which was not going to be a table at all. It was going to be a series of actuators.
Yeah.
But an alternative is we have a table, is to use it in a different way and see what we can get out of it.
Yeah.
And
a few years ago, we had a project with PG&E, and it's a different problem where we have electric equipment sitting on a support structure. It has nothing to do with the soil and the rocking, but the rotation degree of freedom happen at the top of the support structure. This thing is so big, so we just want to put the equipment on the table, and we use the rotational degree of freedom of the table to represent this rotational degree of freedom of the support structure. But because of the communication between the equipment and the support structure, there was a feedback loop, and it was a hybrid test. And we can do the same thing, but for
yeah. Also, this shaking table is controlled by a 469U controller, so all the vertical actuators are controlled independently, so you could actually exercise the pitch and roll degrees of freedom. Indeed, I don't know. In this exercise, it was kind of we were getting to the limit of the shaking table, and I don't know how well we'll reproduce this because there is feedback.
Yeah, the scaling is always an issue because of the mass that you have and the overturning moment. And I understand.
But your point is it's most interesting for the entire community that it is time to begin to look at these rotational components of the ground motions, and yes. Oh yeah.
If you look close at the data, you might even have some rotational components in there.
Yeah, we do.
If you're near the capacitor of the table, it'll begin to rock.
Yeah, and with something we have the accelerometers and there to look at that. Actually, in the shaking table in San Diego, when we tested the 7-story building, we did note very small, but the rotational component is there. And we actually gave that to the blind prediction teams to see if they wanted to have that as part of the prediction, but it did not have a major impact. I think it was of the order of 2% or so of the total displacement at the roof due to rotation.
I think that's because of flexibility in the actuators to have a little bit more if you're near the capacity of the table.
Here, yes.
Forward turning.
Yeah.
Yep.
Yes.
How much viscous damping were you getting?
You mean equivalent viscous damping?
Correct.
Yeah, very little, because we did not have any viscous dampers here. So I'm just teasing you. It's once you have that, it's very, once the system goes nonlinear, it's very difficult to, you lump everything into hysteretic damping and into equivalent viscous damping. So for this case, when you have this, the shape, you're getting of the order of about, I have not computed that, but off the top of my mind, it will be so in between 12 and 15% equivalent viscous damping. And in the very early test where the specimen was essentially linear, it will be very, very low. Did you do any calculation or so? No. It probably be of the order of, or under Y noise, probably 1-2% or so. And in our models, in these cases, we basically try to use as little damping as we can. This is our way of, so everything goes into hysteresis or so, but everyone does a different.
One more question.
My comment or question is related. I was going to say before your comment that my impression these post-tension rocking systems are generally pretty lightly damped, like almost very little hysteretic energy dissipation. So I'm surprised to hear you say 12 to 15% what you think the.
Oh, it comes from it comes from the mild steel. No, from the mild steel. You saw the cage there. I had a cage. We had a cage on reinforcing steel for that purpose because they are so lightly damped that you do need to supplement that.
So that's intentional.
Oh yeah, it is totally intentional. I totally went over that without saying much. But all these bars are there to provide hysteretic damping. Otherwise, it will not be the case.
Mm-hmm. You have to have some source of.
Oh yeah. Mm-hmm.
So that's the intended joint, right? That's
yeah, it's these bars are crossed at the interface, and they have to yield due to the kinematic. That joint opens and takes those bars in tension and in compression. So without them, basically have no damping or so. You rely on a little energy dissipation from the concrete, and it's pretty small.
What's the thickness of the steel shell? Do you keep it thin so that you
It
aren't
was,
so stiff that
I believe in this case it was 1/4 inch thick.
And it's a scale 1/3, so multiply by 3 or so.
Yeah, we get
Yeah.
the criteria for the selecting the shell size is given by Gabriele Guerini, the previous test. I think it was something like the column diameter over 100 should be, I think, the minimum or maximum.
I think the thickness to diameter is about less than 1/90 or so. That's probably some. You were going to ask it?
He asked one of my questions. I had a kind of a tangential potential research is actually providing a socket with almost like when you look at a triple pendulum or just a single pendulum isolator, and you have that ball socket connection. What if you added just a PT at the perimeter with some sort of fireproofing cage around it, so that the PT only takes the lateral load, and the center column with that socket takes all the gravity load only. And then in a seismic event, the PT has to do all the work. Is that like a non-starter because the PT would be in so much stress? You kind of get what I'm describing?
No, but we can talk about that later.
you're going to see a next presentation. Something
So we are following with a project with a hybrid testing or
not
so.
exactly socket, but something.
Oh,
That would be easy.
good. Thank you, Jose.
Thank you.